Okay, so good day, guys. This is our seventh tutorial for chemistry. So we are going to be looking at water and solutions and solubility. So yeah, let's move. So okay, water is a substance composed of the chemical elements hydrogen and oxygen and existing in gaseous, liquid, and solid states. Okay, we know that we can have water as liquid water, the steam, and water and ice. Okay, it is one of the most plentiful and essential of compounds. Very, very important to life, everything we do. So it tastes like an odorless liquid at room temperature. It has the important ability to dissolve many other substances. That's why they call it what the universal solvent. Although the molecule of water are simple in structure, issue of course, the physical and chemical properties of the compound are extraordinarily complicated and they are not typical of most substances found on Earth because ideally, basically, the type of molecular bond found in water is hydrogen bonding is really a strong one. So you get so even though the water the structure of water molecule is really simple, but a lot of stuff happens under the hood with water, higher boiling point and all those stuff. So, for example, although the sight of ice cubes floating on a glass of ice water is commonplace. Such behavior is unusual for chemical entities. For example, every other compound, the solid state is always denser than the liquid state. But in case of water, it was the other way around. So there are just kind of a lot of examples like that. Another one is the anomalous behavior of water, where water kind of um decrease. It's kind of decrease in volume from 0 degrees to 4 degrees Celsius. Then started increasing in volume from 4 to 100. So okay, we are coming to the hardness of water. So what was basically hardness of water? Hardness of water is just basically an effect or something that happens to water when you have some ions present in it. Sure you get. So the hardness of water due to the presence of soluble is due to the presence of soluble what bicarbonates, chlorides, and sulfates of what calcium and magnesium. Let's look at that. Number one, we have soluble bicarbonates, chlorides, and sulfates of what calcium and magnesium. So when you have ions like bicarbonates in your water, you have chloride, you have sulfates of calcium and magnesium. All those ions they tend to what make your water hard. So water which does not give lather to soap is hard water. The water won't foam when you are using it with soap. So that's the hard water. So water is the most important compound that is needed for the survival of life on earth. Yeah, water is present on ocean, rivers, yes. So rainwater is considered the purest form of what of one thing I want you guys to know that it is the purest form of what naturally occurring water. Rainwater is the purest form of naturally occurring water because how does it happen? There's evaporation of water from water bodies, then there's now condensation back. So which is actually the like a process of producing something pure. You get my point. So but the rain while it's coming down, there will be impurities in the air that's going to meet. So the purest form of naturally occurring water, naturally occurring water like river, lakes, all those ones. Rainwater is the purest. But when it's see the purest generally is what it's distilled water. Okay, water can be classified as hard water and soft water. Yeah, for basically under the hardness of water, we can have the soft water and the hard water. So for soft water now, it lathers with soap. Okay, what water which is obtained from the rain is what soft water. That means some things are they are in it already. You get. So this water is suitable for household purposes, for example, laundry and cleaning. Hard water. It is known as hard water because of the presence of salt of calcium and magnesium. Hard water does not lather with soap but instead forms a precipitate. So why is water hard? So hard water has high mineral content. It is formed when water percolates through the deposit of chalk and limestone, which are made of magnesium and calcium carbonate. It does not lather with soap, so it is not suitable for laundry purposes. The hardness of water is harmful to the boilers as the deposition of salt occurs, which reduces the efficiency of the boiler. When you're trying to use boiling ring or all these things to boil or even kettle, you start seeing whitey stuff under it. Shey you get. So hard water is safe to drink, but using over a long interval of time can lead to many problems like the strains in the skin. Water appliances work harder, resulting in higher water bills, spots appear on clothes and linings. Okay, so types of hardness of water. We have the temporary hardness and the permanent hardness. So for temporary hardness now, the presence of magnesium and calcium carbonate in water makes it temporarily hard. In this case, this hardness of water can be removed by boiling the water. Take note of what is causing temporary hardness. Magnesium and what and calcium carbonate. Magnesium and calcium carbonate causes what temporary hardness. So when you boil water, the soluble sort of magnesium hydrogen carbonate actually is converted to magnesium hydroxide, which is insoluble and hence gets precipitated and is removed. After filtration, the water we get is soft water. Okay, permanent hardness now. When the soluble salt of magnesium and calcium are present in the form of chlorides and sulfides in water, we call it permanent hardness because the hardness cannot be removed by boiling. Of course, shey you get. The idea is we have soft water, hard water. So I want to quickly just recap that soft water is kind of like okay, the water you get from rain is what is a soft water. But when you come to hard water now, you now have to type the temporary and the permanent. For the temporary, what causes it? Calcium and what? Magnesium carbonate, and you can remove it by what? Just boiling. And then for permanent now, when the soluble salt of magnesium and calcium are present in form of chlorides, that is what? Magnesium chloride, calcium chloride, magnesium sulfide, calcium sulfide. We call it permanent hardness because the hardness cannot be removed by boiling. We can remove this hardness by treating the water with washing soda, insoluble washing soda. Insoluble carbonates are formed when washing soda react with sulfide and chloride salt of magnesium and calcium, and thus hard water is converted to what? To soft water. That's just it. So it's advantage of what? Hard water. Your soap will not lather, wastage of fuel, formation of scales on metallic boilers. I think I explained that. Removal of hardness of water. How do we now remove hardness of water? So for temporary hardness first now. So by boiling, I already said that. Then the second one, the by Clark's method. So calcium hydroxide, that's the Clark's reagent. Let's note that they can ask that very well. Which of the following is the Clark's reagent? And what's the use? So so sorry for that. Boiling is one method. Then using the Clark's method is the what? Second method. It removes the hardness of water by converting bicarbonate to what? Carbonate. So removal of hardness of water now. This is now for the what? For the permanent. So we have the GAN's permitted method. In this method, the sodium aluminum orthosilicate, known as the permutate or zeolite, is used to remove what? That's the reagent they use. That's the sodium aluminum orthosilicate. That's the permutate. So that's the formula: the Na2Al2 Si2O8 dot KH2O. That's the formula. Yes, you can use it to remove the hardness of water. Then for the second one, Cargon's process. In this process, sodium hexametaphosphate Na NaPO36. You see that already. Known as the as Calgon. So the hardness in water is removed by absorption of calcium and magnesium ions. So we see those two guys there. And also this third guy now, the ion exchange method. Ion exchange resin method rather. Shey you get. So we have the Gans permutate method, which is the what? The permutate, or you can also call it zeolite, or now call it the full name sodium aluminum orthosilicate. Then the Cargon's process, that the one that is using Cargon, which is also known as what? Sodium hexametaphosphate. Then the last one, the resin method, the ion exchange resin method. Of course, we are exchanging ion. So in this method, the permanent hardness of water is removed by using resins, calcium or magnesium ions are exchanged with chloride or sulfate ions. Okay, are exchanged with chloride, yeah. Calcium or magnesium are exchanged with chloride. Sulfate ion are exchanged with anion exchange resin RnH2OH. Determined, yeah, demineralized water is formed in the process. Of course, we are trying to what, remove all those ions, all those minerals from water in order to make it soft. And those are the reactions that apply. So harmful effect of hard water. So some of the most common sign of hard water is, okay, linings and clothes looks dull and feel rough, ugly stains on white buckling and scale build up on faucets, low water pressure from showers due to clogged pipes. So sorry for that. Then chalky or white residue or spots appear on dishes, stains appearing in the shower. Okay, so water cycle. This is just basically to just, it is not really pertaining to the body. Let's just talk about it as far as still water. So water never stops moving. Here's the idea. So the water cycle mainly describes the process of the continuous movement of water from surface of the earth, and it usually carried out in four different stages. The entire cycle is controlled by the sun and is also known as the hydrological cycle. Hydro water. Okay, so the first one is evaporation, second condensation, third precipitation, four collection. So in evaporation now in this stage, heat from the sun heats up water from oceans and other water bodies and evaporates water in form of vapor which rise up and form clouds. Evaporation of water, that's the first method. Then condensation, the water vapor in the clouds cools down when it reaches the cloud. Then after it cools down, what happens to it? It turns to liquid. The cooled what in precipitation, and the cooled water vapors in the cloud forms droplet and released in form of precipitation back into the air surface in form of rain or snow. You know that already. Then collection, the rainwater runs up to the ground and gets collected into the river, ponds, well, and back to the sea. And from the sea again, there's evaporation, condensation, precipitation, collection again into the sea. Again, that's the cycle. So what's not solubility? So this is where it gets interesting. So solubility is the property of solid liquid or a gaseous substance called solute to dissolve in a solid liquid or a gaseous substance. So solubility is just an ability in this case, like okay, you have a solute, the ability of that solute to dissolve in a solvent. So your solute can either be solid liquid or gas. Your solvent also can be what? Solid liquid or gas. That's the idea. So okay, whenever we are discussing the point called solubility, we should have this in mind as okay, solute plus solvent is equals to solution. Your solute is dissolving in the solvent to form what? A solution. So your solubility will now be how much solute can dissolve in a solvent to form a solution. That's the idea. How much of this solute will dissolve. That's the idea. So the main definition and I need you guys to know is this. Solubility of a solute at a particular temperature is the amount of the solute, either in grams or moles, that will dissolve or saturate in 1,000 cm cube, which is also what? 1 dm cube or 1 liter of the solvent at that temperature. I underline that at a particular temperature. That temperature is very, very important because at different temperature, solubility is different. So is the amount of solute that will dissolve in a particular volume or particular amount of solvent, or basically 1 dm cube or 1 liter is what we use here at a particular temperature. So solubility can be measured in gram per dm cube or mole per dm cube. Gram per dm cube when you are using the mass of the solute, mole per dm cube when you are using the amount in moles of the solute. You can also say that solubility is the equilibrium concentration of solute in a solvent. That's the idea. Your solute is in the solvent and they are what dissolved. So you get, they must be dissolved before you can say that's the solubility. You know, some might not dissolve and just be kind of, might be kind of um forming suspension in it, you know. So you get, but when they dissolve, then that dissolution is kind of referred to as the solubility of that solute. So this will let you know that solubility is a fully dependent on some factors where temperature happens to be one of the factors. Other factors include pressure, presence of other chemicals that may cause changes in the pH. Okay, More about solubility. Now that we have basic knowledge of what solubility looks like, let's look at solution. So, as discussed, solution will be the homogeneous mixture of solids and the solvent. That's the idea. Homogeneous. I explained what homogeneous is in the previous lectures. That homogeneous mixtures will be something that they it is not necessary that they are in the same state, but they are in the same phase. You cannot really differentiate between the two. If you put your pinch of salt inside water, you shake it, you make sure it's dissolved, you will not notice this salt at all again. It will be like they've mixed together, and all that's what homogeneous mixture. So we have some common solutions that are given some names. So like the ones that we have names for. So when you have the iodine in ethanol, they call it tincture. Is a solution called tincture. Notice that. They can ask you what is the solvent in tincture. So alkanol and water, that's antifreeze. You have alkanol and water is antifreeze. Carbon dioxide and water is carbonated water. Then rubber and benzene is what vulcanizer solution. So note on solubility now. So in solids, very very important. Don't forget solubility is the ability of a solid to dissolve in what? A solvent. Having now. So and the solubility of different solids will be different. Shey you get? If I put salt inside water, maybe if okay, let me try. Okay, here let's reason it this way. Maybe sugar and salt. I feel salt should be more soluble. So if I put 3 3 grams of sugar inside maybe a cup of water, everything might dissolve, and that might be the solubility. Like okay, 3 grams per maybe 1 gm cube. But for the salt, it is possible that the guy can take more than the 3 grams. Shey you get? So when you now have more grams of salt entering, so that means you can say the salt is having higher solubility there. So the solubility at this point also now depends on what on temperature. So when you increase temperature, solubility for solids, when you increase temperature for solids, solubility increases, while when you increase temperature for gases, their solubility decreases. And when you decrease temperature for solid, their solubility also decreases, while when if you decrease temperature for gases, solubility will increase. Okay, that's that for that. In all solutions, the substance present in the greatest amount will be the solvent, while solute will be of lesser amount. Of course, we know that already. So we have three major types of solution: unsaturated solution, saturated, and supersaturated. Unsaturated solution is a solution that contain lesser amount of solute that than it can actually normally contain. For example, like let's say for example now, when if you pour 10 grams of salt inside water, it contain it, and that's the maximum it can contain. Shey you get? So that means unsaturated will not be that maybe I pour 5 inside it, whereas it can still take 5 more. So unsaturated is when you have lesser than it can contain. Saturated is the one okay when you have 10 oh it has 10 grams, that's the one it can contain, that's it's saturated already. Supersaturated is now when it has more than, and that's more than, it contains more solute that it can contain at a particular temperature. That this is formed when the saturated solution is cooled and it has more than maximum amount of solute that it can contain. Not all salt can form a supersaturated solution, knows that. Please also note that. And how do we form it? Um, when you reduce the temperature of a saturated solution. So note on solubility, we have true solution. We have three kinds of solution now. The true solution. I hope I didn't jump on the slide. Okay. So we have the true solutions, we have the colloidal solutions, and we have the suspension. These are ideally we have two types of solution: the true solution and the false solution. Then under the false solution, we now have colloidal solution and suspension. So for the true solution now, these are homogeneous mixture of two or more substances with a particle size less than 10 nanometer. Please note that the particle size for true solution, the particles of the true solution, their size is what? Less than 10 nanometer. Very, very small. You can't see them. So example is sugar solution because they are soluble, air, brass, copper, among others. You can't use your filter paper to separate the particles of a true solution because the particles they pass through the filter paper, they are so small that they will pass through. So colloidal solution is the second one, which is under a false solution. So colloidal is a mixture of homogeneous in appearance and heterogeneous in nature. When you look at you will be thinking it is what, it is a true solution, it is what, it is like all the everything, they are in the same phase, but normally they are not. Example is your blood. You will not be able to separate the particles, everything in your blood, shey you get, except if you use centrifugation. You cannot differentiate between this is the water, this is the plasma. No, no, they are all in the same phase, but it is after centrifugation that you can do what, know the kind of difference. So that's the colloidal solution. So they look homogeneous when you are looking at them with your eyes. They are homogeneous, but their actions, everything they do is like what, heterogeneous. Of course, they are truly heterogeneous, but what we see them as is what, homogeneous. So this is a mixture of particles that can be seen with the naked eyes. The particles of colloid are bigger than those of true solutions. Examples will be discussed in next. Okay, yeah. Solution, suspension now. This heterogeneous, they are heterogeneous normally. So it is like we are coming from homogeneous and heterogeneous, then heterogeneous. Okay, that may not even be regarded as solution because the solid doesn't dissolve but gets suspended in it. Like for example, chalk solution. When you have chalk in solution, the chalk is not dissolving. The chalk is just suspended. When you put it down, what happens to it? It will settle. So out of these three, it is only suspension that can settle while standing. Okay. So for colloidal solutions now, so just let's just take the solute as the dispersed phase and the solvent as the dispersed medium, or dispersion medium or dispersion phase. So you get dispersed phase and dispersed medium. So when I say dispersed phase, I'm referring to the solute. That's what they use. When I say dispersion medium, that's the solvent. So, but there's a mnemonic so that you won't get this out of the way. So let's follow God like little relevance in life. So the ones I underlined are the words colloidal solutions. So follow there represents fog. Okay, yeah, I think I did that already. Follow represents fog, like represent ladder, elephant represents emulsion. So what are the dispersed phase and the dispersed medium? So the dispersed phase, which is the solute for fog, is liquid. How do I know that? Look at what is behind follow. It is let. It starts with L, so that's liquid. Then what is after follow is G, that's God. That means for fog, which is follow here now, it is liquid in gas. Do you get my point? Just the one before it and the one after it. Then for like now, which is ladder, it is gas in liquid. While for elephant now, which is emulsion, it is liquid in liquid. Very simple. So another two mnemonics now, shey get. So we have some solars and some smoke great. So for just the same thing, so and smoke is what we are using here. So for some solars, the so there stands for sol, and this means it is what, solid dispersed in liquid. SL, some and less. So some so less. The so there is sol and is what, solid dispersed in liquid. For smoke it is what, solid dispersed in gas. Some and great. So the summary now, colloidal solution, fog, ladder, emulsion, sol and smoke. So we have let's follow God, of course. So dispersed phase is liquid, dispersion medium is gas. That's for fog. For ladder we have gas and liquid. For dispersed and dispersed medium respectively. For emulsion we have liquid, liquid. For sol we have solid, liquid. For smoke we have solid, gas. These things are very very important. So colloidal solutions, properties and notes. Okay, so stability. Okay, stability first. Okay, yeah, that's the first now. It's colloids are relatively stable in nature as the particles of the particles are dispersed, unlike suspension, where it's going to settle. These guys are not going to settle at all. Good. So ability to pass through ordinary filter paper with ease. They pass through without filter paper. But when it comes to ultra, ultra filters for filtration, they got caught. Yes, when it comes to ultra ones, like the ones that are very, very high that can se- that can separate um particles of that size, they will be caught. And then they have ability to scatter light ray. This is one um of their heterogeneous characters. When you shine light into them, the particles will be reflecting the light, be scattering the light. Shey you get. That's one of the reasons to know that it is actually heterogeneous in nature. Okay. Okay, heterogeneous in nature since they consist of two phases, dispersion medium and diffusion phase. Hence, it's said to be what, heterogeneous. I think you know that already. Then homogeneous in appearance. For the fact that they are heterogeneous in nature, they are said to be homogeneous in appearance. This is mainly because the suspended particles are so tiny to be seen with the naked eye. So note that solid will be dispersed in solid in alloys. Yes, alloys is what? Metal mixtures of metals. So it is solid dispersed in solid. So fog, mist, and cloud belongs to the same family of liquids dispersed in gas. Emulsion and milk are what? Liquid dispersed in liquid. Butter, gel, paste, cheese, and salt in the same category. They are solid emulsion and they belong to what? Solid in what? In liquid. Emulsion is liquid in liquid. Okay. So for suspension now, these are also heterogeneous mixture where the solutes are suspended instead of what? Dissolving. The solutes are suspended there instead of what? Dissolving. I think I said that already. For example of that chalk solution, the size of the particles here are quite large and large to be seen with the naked eye. Like actually, you still see it. You see those particles. You can see the particles of your suspension, like that of chalk. Suspension is said to be unstable as the suspended particles settle easily while standing. The ability to scatter light ray owing to their large particle size too, they also scatter light ray. Of course, we expect that. So the summary now, so we now have colloids and suspension. Okay, true solution, that's the one I call the solution, then colloids and suspension. So the size range for solution is 3 10 to the power minus 9, for colloids is 10 to the power minus 8 to 10 to the power minus 6, for suspension is 10 to the power minus 5 to 10 to the power 10 to the power minus 3 actually. So the set while standing, yes, yes, no for solution, no for colors, but yes for suspension. Tyndall effects, no, yes, yes. I explained that because of their particle size. Filter paper, pass through filter paper, yes, yes, no. Colors also pass through filter paper, except when it comes to ultrafiltration. Then the face, they are homogeneous. But colors, you know that they are in nature they are heterogeneous, but in appearance they are homogeneous. The suspension is what? Heterogeneous. So let's now look at the calculation aspect of solubility. It's actually getting interesting from here now. So we've discussed this definition and everything, the theoretical aspect. So let's now look at the calculation aspect. And if you remember this formula, so this definition rather, solubility of a solid at a particular temperature is the amount of the solute either in grams or moles that would dissolve or saturate 1 dm cube or 1 liter of a solvent at that same temperature. That means so a solute is dissolving in the solvent, having in the volume of a solvent. So we can say solubility is equal to what? Amount of solute that is dissolving over the volume of the solvent itself. Yes. So solubility equals to amount in mole times 1/volume. That still makes sense, right? I just kind of separated them. Then, so don't forget amount is what? Mass over molar mass. So we can also say, now say solubility is what? Mass of solute over molar mass of solute. Abina times 1/volume of solvent. Makes sense. So that volume we are using here is what is in dm cube, but they say most of the time the volume you be given is cm cube, so you have to convert. But for the formula to do the conversion for us itself, that you just put 1000 in place of that one, then you are good at the formula for solubility. In fact, it's like an almighty formula. So let's look at some solved examples now. So 100 cm cube of a saturated solution of this, that's the mass, the volume of the solution at large at 40 degrees Celsius is evaporated. They evaporate it. 14 grams of solid were recovered. That means the grams of solid in it was 14 grams. What's solubility at that temperature? We have 14 grams of KClO3 in a solution of 100 cm cube. That means the water there is 100 cm cube. So how do you now do it? Mass over molar mass times 1000 over volume. What's the molar mass? You calculate it, you add it together, you add their respective atomic masses together. Then the mass of the solute is 14 grams. The volume, the volume of the solvent is what? 100 cm cube, and that's it. So let's move on to the next one. So coming to the next guy here. So coming to the next guy here. Um, you can also have solubility to be in grams per 100 grams of solvent. Yes, it is not compulsory that it is always solvent must be in volume. No, it can be per 100 gram. She get per something per all those ones. So but it's because the most common cases are what? GM cube, that's why the volume is always there. So all you need to do is divide the mass of the solid by that of the solvent and multiply by 100 gram. That's one case actually. So you get, for example, calculate solubility of sodium nitrate. It 21.9 grams of the salt is dissolved in 25 grams of water. So solute over solvent times 100. That's all you need to do. Do you get my point? It's like you want to calculate percentage basically if you are using 100 gram. If it's per 500 gram, you multiply by 500. That's the idea. So solubility products. So that the other one there is just question of normal solubility. But when it comes to solubility products, it's actually a bit technical. It's a bit technical, but it's too simple actually. So real products is just like a kind of equilibrium constant. So I'm not supposed to introduce this now, though we are still going to talk about it in equilibrium constant. But after the equilibrium constant, it's something you can still come out and try to, oh, this is why this is this. But I'm going to still say everything now. I'm going to say everything now. So real products is like a kind of equilibrium constant where we consider just the dissolved species and gases. Yes, it's just like don't forget a solid is dissolving in water. Shey you get. So when after dissolving it's going to ionize. In fact, salt when we in the next lecture that's where we talk about um salt as what? Ionic compound. So they ionize. Shey you get. So if you have something like sodium chloride you form what? Na plus and Cl minus. That's the idea. So it is those dissolved species and also if you have gases that you can consider your what solubility product. So in fact we call solubility product or solubility what product constant. Okay, good. Yeah, we call the solubility product the what solubility product constant. So we can also say the equilibrium, it is the equilibrium constant KEQ when an ionic substance dissolves in water. Yes. Equilibrium constant is actually kind of different. Like we have the dissociation constant, acid dissociation constant, base dissociation constant, KKB, KW, pressure the equilibrium due to pressure for gases and all. So but this one is just when any substance dissolves in what? In water. Or it can even be it might not even be water. That's when we talk about the common ion effect. We're also going to look at that. So for instance, when your salt Na2CO3 dissolves in water, it nice to give three ions actually, but two. It's going to give me two Na plus and what? CO3 two minus. So we can just say two ions, Na and CO3 two minus. So we have this. Na to CO3 is giving me two Na plus and CO3 two minus. With this, we know that what exactly happens when an ionic compound dissolves in water. That's it. When an ionic compound dissolves in water, it differentiates, it kind of dissociates rather into what? Its constituent ions, the cations and the what? Anion. Note this that sodium chloride does not have solubility product owing to its what? High solubility in water. Please note that. So solubility products again, we have these. We call solubility products constant KSP now. That's the symbol. It's the equilibrium constant when an ionic substance dissolves in a solvent. So note for this, for your equilibrium constant, the formula for equilibrium constant, when we only consider gases and dissolved species. So KEQ will be what? Product raised to the power of product mole over reactant raised to the power of what? Reactant mole. So from the reaction above, from this guy here. So the mole of 2Na plus is 2, while that of CO3 2 minus is 1. Hence we can say the solubility product will be what? Um since let's look at something here. Since this reactant, don't forget it's only salt that we are dissolving. So the reactant is solid, so we are not including it at all. So you get, it is only if it is what? Aqueous or what, or gas that we consider. So then the reactant is the product is what we are interested in now. That's why your KEQ there is the only product you have. So the concentration of Na plus is squared because of the 2 that is behind Na plus in the equation. Then CO3 2 minus is power 1. The reactant would have solid as the reagent as you will most likely be dissolving solid in liquid. Do you get my point? That's the idea. So the solubility product constant now. So in solubility product, the expression will give rise to multiplication of at least the concentration of two ions. Each will stand for the solubility. That's it. Each will stand for solubility. The multiplication of both can be referred to as the solubility product product. See, each ion stands as what, as solubility. So when you're now multiplying to solubility, you are looking for the product, that's solubility product, which can then be referred as KSP, solubility product constant. From the example given above for Na2CO3, this, okay, if solubility of Na2CO3 is 0.12, then that of Na plus will be 0.24. Why? Because it's 2 Na plus. And that of CO3 will also be 0.12. Why? Because it is the same mole with Na2CO3. So where KSP involves the modification of the solubility of both ions. Enough of this. Okay, yeah, let's move on. Just move on to the next page. So um, let's try for a sort. Just the expression here, the main calculation can be done easily, and the explanation, okay, yeah, that's it in the video, like you have it right now. So for example, number one, what is the expression? What is the expression? Yeah, for the solubility product of good chloride in distilled water. When I say expression, it's just the formula that you get at the end of the day. The idea is all you always have is that KSP can either be equal to x squared or 4x cubed or 27x raised to power 4, something like that. So you have an expression like that if, for different sorts, different expression for different sorts. So in this case, now I want to use AuCl to give me gold and chloride ion. So if the solubility of gold chloride is X, okay, of course that's what we are using. So the soluble product will be what? Product is per product. You know why the reactant is left out? Because they most likely be solid. So we now have gold and chlorine, their concentration multiplied together. So there's no index for both ions because their mole is equals to 1 each, of course. So we have gold chloride is X, Au is X, chlorine is X. So the equation we are now going to, the reaction we are going to get overall will now be what? KSP equals to what? X times X, have you now? So that's it. So we can now say KSP is equals to gold times chlorine, which is X times X. That means KSP for gold chloride is what? X squared. That's the idea. So the KSP will be equal to the square of the solubility of salt that we ionize to give 1 mole of the cation and 1 mole of the anion. If it is 1 mole of the cation, the positive one that you are getting, and also 1 mole of the anion, your solubility product will be X squared. That's the idea. So, and input the value of if you now want to calculate maybe the KSP, they can ask, okay, if the solubility is 1.1 molar, you just put 1 in the place of X. If they say it is 0.5 molar, put 0.5 in the place of X. You get my point? That's the idea there. So, this example two. What is the solubility product expression for lead chloride salt in distilled water now? So, it's still the expression actually, you get. So we have PbCl2. So Pb will be X, Cl2 will be 2X. That's the idea. So then from there we can now say Pb2 plus than Cl is power 2. Please note that because of the two moles behind it. So we can now say, okay, KSP is what? X times 2x squared. In fact, that's it. The concentration of chlorine here is 2x. Then you have to also square it. The concentration is not what? It's not x. As you can see in the equation, we have 2x as the concentration. And after the concentration, you have to still square it with the mole. That's what we did there. So KSP is now equals to what? 4x cubed, where x is what? The solubility of the salt. So if they say, okay, what is the solubility product of 0.005 molar solubility lead chloride, you can just put that 0.005 in place of X and you get your answer. So you can also do, it's possible they also give you KSP and ask you for solubility. So it's just a two variable kind of equation. You can always work on this. So I gave out these, and you for good chloride, good 2 chloride, good 3 chloride, iron 3 chloride, potassium phosphate, sodium carbonate, all those guys. So just try to do them yourself and see what you get. In fact, most especially try that last one. So moving on to the next. So for the ones we've been treating, it is when they are dissolving in water. But here now it is possible they also dissolve in other reagents. So other reagents like maybe, but anyhow, the reagent they are dissolving in, we have the same cation, the same anion with the solids. That's the idea. And that brings in the idea of what? Common ion effect. So, yeah, the dissolution of substances or solute in a solvent that an ion in common with them, like CaCO2 dissolving in what? in HCl because chlorine is common to them. Sure you get. So Na2SO4 dissolving in H2SO4. So that's common ion effect. So that's the idea behind common ion effect. So for common ion effect now, so common ion effect can be actually be somehow confusing, but it's still just very very basic. Sure you get. So but I'll be definitely available if you have any question on it. Sure you get. In fact, maybe today I'm going to look at it very well. So the only thing that we are just adding to our knowledge, that our knowledge of solubility products, is that the ion that is in common, you have to bring it in. Shey you get. So for example now, look at that HCl. But if, okay, I think I gave you guys a common. Okay, what is the expression of solubility product of 0.01 molar AuCl in 0.1 molar HCl? So but the solubility of AuCl is 0.01. So we have that 0. Okay, for AUC, I first kind of did out of what HCl, which is 0.1, 0.1, 0.1. You know how everything became 0.1 because they are all 1 mole each. So chlorine is what is common to them. So it's only chlorine that we need. It is the only common ion that we have here. So now let's now do our normal solubility product normally for AgCl. So it will be what X. Then for chlorine, instead of writing just X, shey you get, you write what X plus 0.1. Why do I put the 0.1? Because the chlorine from the HCl will also come and add to it. That's the idea. So we can now say UCl, okay, x plus 0.1, then KSP equals to x squared plus what? 0.1 x. Do you get my point? So where your okay, yeah, I said I dropped a tip there. So actually, if they gave us the 0.01 here, so you can easily use that to calculate your KSP. So you get, but there are cases where they won't give you. They will ask you for the solubility itself, go, and they will give you KSP. So in those cases, you will most likely fall into quadratic equation. Although this particular concept is not part of your syllabus, though, so you get, but it's just something they ask question on solubility product, but not the calculation. Do you get my point? But the calculation is just showing you how an ion from another compound is contributing to the ion of the solid. That's just the idea. So when you have it in that case, for anything, for a compound to have solubility product, that means the solubility is low. Do you get my point? So and if the solubility is low, it might be 0.00 something like that. So you get. So now imagine we have look at what I did. I said KSP is equals to X close bracket, then X plus 0.1. Then and I said, okay, I think I multiplied throughout. But if you now want to just, if you don't want to waste time, because this is already a quadratic equation, if you don't want to form your quadratic equation, X plus 0.1 would be something very, 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 like it should still almost be the same thing as 0.1 because X for that compound will be very very small. See, because it has solubility product. So x can be 0.001. So 0.1 plus 0.001 is 0.101. It is still like 0.1. So you can just ignore it and save yourself the stress of what? Working on quadratic equation. So that's all for this class. Thank you.